Snoop Dogg made a bike sticker. Doesn't even remember. I remember. He lived it every single day. And Julia got me JoJo Siwa stickers, but also bike stickers for my birthday.
What was the gift? Just a sticker?
I don't know, I think it came with the camera. That's also in my room.
The toy camera?
Yes, that broke.
Okay.
All right, here we go. What's that on the board right there? What are those things?
The dots.
The dots?
Yes.
Okay.
Lewis is.
Lewis.
Lewis dot structure says it right there, right?
Yes, it's dots.
What's the purpose in a Lewis dot structure?
It's shorter range than
Reading the top line. Represents number. What's the purpose of the dot structure?
To represent the number of valence electrons.
Well,
This is tasty.
Constant grounding. Left on it.
all right, so the purpose of a Lewis dot structure is to represent the number of valence electrons. Let me get something out of that.
Well, chemistry tools. It's like Mickey Mouse.
He definitely forced me to be baseball rather than. He was like, you could not kill me to be baseball.
Oh, yeah, no. I was telling her yesterday, she was like, I would cry if someone said that you do Beast Boy.
I was literally showing her a picture proof. Nobody said that. She said.
Oh, real, let me show all this Beast Boy.
I didn't say that.
Oh, that is Beast Boy.
Nobody forced you to be baseball. Okay?
I want to be Beast Boy. Let me be.
All right, here we go.
Compression shirt.
Okay, so we need to know how to draw those little structures, okay? Give me some fairly easy questions on the test. We ought to be able to do that. Okay. All right, here's a diagram that's showing the relative sizes of neutral atoms to their stable ion. Let's ponder this just a second. The gray and green spheres on the left represent metals and their cations. So the gray on the left three columns would represent, for example, top left-hand corner, that's lithium, and then the little green, the smaller green sphere is a lithium cation. Okay, so a couple of things we need to take from that is that the cations are smaller than the neutral atom. Okay, and then also we can see the periodic trend there of how they get larger as you go down a group. So the sodium is larger than the lithium, and the potassium bigger than the sodium, and the rubidium bigger than the potassium, and so on and so forth. Okay. All right. If you look and see, like for instance, magnesium and sodium. Magnesium is smaller than sodium because it's got more protons, but it's not that much smaller, right? It's just a little bit smaller, but it is smaller. If you look on the right-hand side, you're seeing the formation of anions. So the gray sphere is, for example, top right-hand corner, a neutral fluorine atom, and then the purple sphere is the fluoride anion. Once it gains an electron, that's how much expansion you get because that electron repels the additional electrons. So everybody spreads out. It's considerably larger. Just to give you a little relative view of it. This is going to be important in a little bit. Okay, I'll come back around it. The size of ions and the charges of ions and what difference it's going to make. In a little bit. All right. One second.
Your tint is out. With high five you. You put your hands on your head. Once in motion, couldn't stop.
Oh, you have to look back and try to high
I
five.
heard.
Yeah, no. Just listen. Do it again. I'm not letting you hit it. I'm not gonna hit you again. So you have your hands connected, right? And they're out. So I was gonna high five. When I went to do that, you put the ball in your head.
All right, all right, let's put a couple things on board here, so. We'll talk about that over there. So we're gonna talk today about ionic and metallic bonding. So let's start with ionic bonding. We're gonna have to talk about it a little bit together because we're gonna have to do some comparison to make it make sense. That's a sodium atom, correct? Lewis dot structure, got one dot, right? One valence electron. A chlorine atom would have 7 dots, correct? 7 valence electrons. Neither one of them have 8. Everybody wants to have how many? 8. Neither one of those guys have 8. Okay. So that wanting to have 8 or needing to have 8 is called what? Octet rule. Okay. So everything that happens in chemistry has got something probably most likely to do with the octet rule. So what's going to happen is this chlorine is going to take this electron away from sodium. Now, sodium, we talk about sodium giving an electron to something, and that's really not the way it works. It's really something that has to take it. Now, sodium's not going to argue with it very much. Sodium would like to get rid of it, but it has to have a substance that can take it away. A non-metal that'll take it away from the metal. All right, that's going to leave us with sodium with no dots and a positive charge, and a chloride with 8 dots and a -1 charge. Now, anytime we draw a Lewis structure, we'll get more into this later. The Lewis structure that has a charge, we'll put these little square brackets around it. All right, and what do positive and negatives do to each other? They attract each other, okay? So the attraction between those two is the ionic bond. So they are now going to be ionically bonded. A couple of examples. Here's a couple of crystals of sodium chloride. A bit larger than what we're accustomed to. Sodium chloride is table salt, correct? Right, where that. Okay. So here's some larger crystals. You may ever have rock salt. You might make ice cream, homemade ice cream, using rock salt, right? That's sodium chloride just in bigger chunks. Just hasn't been ground up as small. And that's almost what this is. This is a little bit in between rock salt and table salt. It just hadn't been crunched up. Okay. But this little crystal of sodium chloride has trillions of trillions of trillions of sodiums and chlorides in it. Okay? I dropped it. Pick another. Okay. So trillions and trillions, all right? And they're all attracted to each other. They're all stuck to each other. Okay? Those cations and anions form what's called a crystal lattice. That's an important term we need to know. And here's sort of what it looks like. It's this alternating three-dimensional arrangement of cations and anions. And that's what I've got in my hand right here. Okay? It's a big crystal of sodium chloride. It's hard to fathom exactly how many cations and anions are in here, but it is a lot, more than you could ever count. Okay? Just in this one little piece. Right? We'll talk more about that in a couple of units, about how many numbers of things we have. Now, there's certain characteristics about this. Okay, obviously it's a solid, right? Okay, we usually also think of metals as being solids, correct? Okay, but there's some differences, right? And there's some differences in this and a covalent substance. So remember in this unit, we're going to talk about 3 different kinds. We've got ionic, metallic, and covalent. So we're going to have to talk about all 3 a little bit here just to compare them a little bit. Back here, I've got my regular glass of water, okay? There are trillions and trillions of water molecules in this glass, right? Okay? The difference in the trillions and trillions in here and the trillions in here is that these are separate individual molecules of water that are all independent of each other. Now they're kind of sticking to each other for reasons we talk about next semester. They're sticking to each other, but they're not all bonded to each other. And that's, if we could shrink ourselves down to the atomic level, then you could easily just pick out individual water molecules and throw them away. You're small enough to do that. Okay? You can't do that with this. Okay? So the difference is we draw things like this, and then we draw stuff like water, and we'll talk about why I'm drawing it the way I'm drawing it in a couple more days. But we draw a picture of water, and that's much more accurate representation for water, because water does exist. It's just a single individual molecule of oxygen and two hydrogens. That glass of water has trillions and trillions of those single individual molecules. Okay? This crystal of salt doesn't have a cation and an anion, just that's it, right? There's trillions and trillions, they're all stuck together, and they're not really ever independent of each other. Okay? They exist as that lattice structure. And that makes for very, very different properties. Okay? Properties of ionic compounds first is that they are brittle solids. We're going to compare this to metallic solids here in just a minute. Okay? They're brittle solids. They do not conduct electricity. Talk about what that means. As a solid, they do conduct when dissolved in water. About that in just a second. Okay? And they are generally poor conductors of heat. All right, now, what does it mean to be brittle? Fragile, okay? It's kind of fragile. I don't know if I can break it. Crumbly, that's kind of a good word for it. Have you ever heard the word malleable? Malleable would be the opposite of brittle. Okay? So metals are malleable solids. Okay? They do conduct electricity. And they are good conductors of heat. All right, so these are two different things. These are ionic compounds. These are metallic substances here. Okay. I think that has two T's. It's got two L's. We'll go with that. All right, so I had a paper clip up here. Let me get another paper clip. All right, so this paper clip, I can bend it, right? Shape it. This is malleable. It's a metal. Okay. So metals are malleable. This ionic crystal of salt, I can't do that to it. I can't bend it or shape it. If I hit it with a hammer, I could crush it. If I hit this paper clip with a hammer, I would just flatten it out. Okay. So you can hit them both with a hammer, but you're going to have very different responses when you start trying to shape them into something. This can be shaped. This is not going to be shaped. Okay. All right. The conduction of electricity. What is electricity, by the way? You know, took physical science, probably played with some batteries and stuff, right? No, never. Never hooked batteries to a little light bulb. Somewhere, 6th grade, I don't know, somewhere. all this anti stuff. You don't think that's something.
I came back from the truck.
So what is electricity? Huh? Energy? Okay, yeah. It's flowing charges. Okay? It's flowing charges. The reason that a salt crystal cannot conduct electricity is that these charges are stuck in place. Now they're vibrating, but they can't move past each other. So they can't conduct electricity. A metal has free-flowing charges. So we're going to switch to a picture of a metal. So metals have a much different bonding arrangement. We took a solid piece of sodium. So let's just imagine our sodium ion, our sodium atom here, who doesn't have a nonmetal to take its electron away from it. What does it do? Well, it basically just dumps its electron off. It just says, get out of here, I don't want you. Okay? Drops it off. So where does it go? Well, it just goes wherever it wants to. It becomes delocalized. Remember that word in the definitions yesterday, right? Its electron becomes delocalized, which means it just kind of floats around wherever it wants to be. Okay? And that makes this lattice here very flexible. It's like these metal cations are floating in a sea of electrons. It's often called the electron sea model. Okay? It's just a delocalized electrons. And that allows you to bend the metal. I can take this thing and twist it around. Okay? But it also allows it to conduct electricity because these electrons, these charges are free to move. All right? If I took a great big chunk of salt and stuck it in the wall socket right here, nothing would happen to me. Okay? If I take this paper clip and stick it in there, got a problem, right? Okay, it's going to get me. Okay? Because I'm a good conductor of electricity because I've got cations and anions floating around in me. Okay? Will this water conduct electricity? This will, but is it water? Is this pure water? Got it straight out of the sink. It's not pure water. So if you had pure water, would it conduct electricity? No. So pure water, so water does not conduct electricity. It's the ions that are dissolved in water that conduct electricity. So I've got a jug of distilled water back there. That won't conduct electricity. I'm not going to trust it because I bought it at Walmart, and I don't know if it's really distilled or not. It says it is on the label. Okay, we're going to go with that for me, but I'm not going to do a life or death experiment with it. But it's supposed to not have any ions in it. It's supposed to have them all removed. Okay, which means it shouldn't conduct electricity. Theoretically, if your swimming pool was full of distilled water, you wouldn't have to get out of it when it became a lightning storm. Okay? Now, your swimming pool is full of numerous ions, both natural and what you add to it in terms of chlorine tablets and chemicals and stuff. So it's very dangerous to be in a swimming pool when it's lightning, because that solution that you're swimming in is a very good conductor of electricity. Pure water is not, but you're not swimming in pure water, you're swimming in a solution. And I'm not drinking pure water, I'm drinking a solution of water and whatever natural ions are in this water based off the geology of wherever the well is that they got it from, the city of Jacksonville. Okay. All right. If you drink just distilled water, it's actually bad for you. If you're stranded on a desert island and all you have is a case of distilled water, it'll kill you. Because it dilutes your bloodstream. And your blood cells try to match that dilution, and they soak up water, and your blood cells start to rupture, and you become anemic, and you become dead. In that order. Yeah. I think you go that way.
In that case, then what's the point of even putting in the effort to make it?
And distilled water?
Yeah. Some
devices, like they sell it at Walmart for things like humidifiers, aquariums, some people put it in aquariums and stuff. But different little, any kind of little gadget that water evaporates out of, if you use regular water over time, you're going to get a salt build up. Because when the water naturally evaporates, it's going to leave the ions behind. So you're going to get this little white film whatever the device is. So you want to use distilled water. Try to prevent that. We have it here for the lab. The labs we do aren't precise enough to really matter, but technically when you're making a chemical solution, you should use distilled water. If we wanted to dissolve that chunk of salt into some water, we want sodium and chlorides in the water and not the other natural things that are already in the solution. But not that we have any instrumentation back here that looks bad. It's just a technicality. Okay, now, if I took that salt crystal and dropped it in my glass of water, what would it do? It would dissolve, right? Okay, write this down. This is a very important statement that we will have to remember many, many, many times throughout the rest of the chemistry life. Ionic compounds dissolve by dissociation. Dissolve by dissociation. Hopefully, I forgot to take up your cell phone. You're not cheating back there, are you?
No.
Okay, thank you.
I'm struggling though.
Okay, well, that means probably not cheating. Just increases the level of temptation. All right, so what does it mean to dissociate from something or somebody? Get away from them, right? Okay. So we use this example first period. I did it it's kind of a risky example. I've got myself in trouble with this before. Okay, but you know, you could say that if you break it up with your girlfriend or boyfriend, that y'all have decided to dissociate from one another. That would sound like some kind of very legal talk or something like some kind of like two lawyers for breaking up. You know? We're going to dissociate from each other's presence or whatever. Reason that's risky is one time, this is a true story, several years ago, I had a girl sitting in about the second row, and I was using the example of dissociating and getting away from your boyfriend or girlfriend. And then I used the example of, in a minute we'll go back to that picture about how salts actually dissociate, is that the water molecules pull the cations and anions apart. Okay, so if you want to continue with the metaphor, they basically start cheating on each other with water, right? Okay, and it dissociates them, as you know that normally does, right? Well, girl starts busting out crying in the middle of class. What I didn't know was her boyfriend had cheated on her the day before. He's like sitting 2 rows behind her, and it's just this whole deal, you know. I had no idea. I'm just trying to make an example of it. I thought teenagers could relate to. Some people related to it a little bit worse, you know.
Right.
They were really, really related to the point of emotional connection. And I'm like, yeah, I messed up there. But anyway, it's
But it'd be me.
too bad, you know. Anyway, you dissociated from your significant other due to their attraction to other particles. And I'm sorry. I've heard that happens. I mean, you know.
Have to be married.
Yep, happily married. 23 years of associations.
That's great.
All right, let's see. So what happens is, if I take that salt crystal and drop it in my water, which I'm not going to do because I don't prefer my water that salty. But if I did, let me flip back a slide for the other picture. Then the water molecules are going to start pulling on the cations and anions in this salt crystal. And it's going to dissociate them from each other. So the greens and the purples right there are going to get pulled apart by the water. All right, so one water molecule, for example, would grab this purple sphere and pull it this way, and one would grab that green and pull it this way, and a purple one this way, and a green one that way, and then eventually the whole thing gets dissociated. And now you have a bunch of what we call free ions, okay, floating around, right? Okay, so always try to find the good in something. You do end up dissociated from your significant other. At least you are now free, according to, it's supposed to be a good thing, right? Freedom. Huh?
Have a night on the town again.
And there you go. You're free to go.
Right.
Do whatever. Okay. So in chemistry, we call those free ions. They're now free to do whatever they wish, right? That includes conduct electricity. So if I had a glass of distilled water and I put a salt crystal in it and it dissociated, then that solution will now conduct electricity because the cations and anions can move about. So if you stick an electrical device in there, then that charge can flow through the water. And you would get electric. Okay. So, and again, we are conductors of electricity. We're actually one big electrical system in a way, right? So your nervous system acts on all the electrical impulses, and including how your heart beats, right? So your heart beats when it beats because your brain is giving it a little jolt. It makes it basically contract a little bit, right? Just like if you touch, what happens if you ever been electrocuted, anybody ever touched electric fence or something like that, right? It basically makes you kind of lock up, right? You've seen somebody get tased, they just lock up and fall over. That's basically what your heart's doing. Way oversimplified, but the electrical impulse, and it makes it kind of convulse a little bit and pumps your blood around, right? So if you take too much charge in, like you get struck by lightning or something like that, then that's going to literally fry the system, just like my TV got struck by lightning one time years ago, right? So it's too much charge. Sitting there watching TV in a lightning storm, lightning strikes, and the TV goes boom. That's it. On new TV, right? Because it's too much. It just fries all the circuitry. If you get struck by lightning, that's literally what it does to you. It just fries all your circuitry. You're just done. You know what?
You made it sound like your TV itself got struck by lightning. Really
Well, not like it is like something in the window.
Your TV got struck by lightning.
The lightning struck like out in the yard somewhere. You know?
You.
Struck a pole, you know? It's pretty cool. It came through the window and just blew the TV off.
Would you watch TV in your yard? Like,
Blew it out of the house, yeah. No, I was in the house, the lightning hit down the street, and the TV just popped. And that was it.
I was about to ask if you had like a really long wire sticking out of your mouth.
Yeah, we just get that one channel. We just watch the, you know, the one that's, you know, Southern television. And, anyways, all right. So, ionic compounds, because of that structure right there, are brittle. They don't conduct electricity unless you dissociate them in water, and they're poor conductors of heat. A metal, we flip back to the other slide, is a malleable solid that does conduct electricity and is a good conductor of heat because it has the ability to move around. It's flexible, or what, if you want to use that word. All right, now, ionic compounds are also known to have relatively high melting points. Let's talk about that just a minute. Let me get y'all to Google something for me for a second. Let's talk about what it means to melt something. Just take that example of that metal right there, because metals can be melted. It's a little easier than ionic compounds can. So if you take a metal, and you're going to melt it, let's just say we put this in a furnace, this little paper clip, and we're going to melt it. What we're doing is we're heating up the substance and making the particles move faster. So those little cations are sitting there vibrating, okay? We're going to make them vibrate a little faster and a little faster to the point that they can start moving past each other. They're still kind of stuck on each other, right? If you separate them completely, that would be boiling it. With vapor, I turn it into a gas. But a liquid, they're moving just around each other, okay? In a solid, they're stuck in place, okay? So if you're going to melt a metal, you just heat it up till they start moving past each other. Usually a little easier to do than an ionic compound. So ionic compounds normally have melting points that are higher than metals oftentimes. It's not always true, but relatively so. All right, but an ionic compound, if you're going to melt it, how hard is it going to be to do it is dependent on two things. Okay, the size of the ions and the charge on the ions. So y'all do this for me right quick. There's three compounds. Lithium fluoride, sodium chloride, magnesium sulfide. Google their melting points right quick in Celsius. In the Celsius temperature, their melting points. Take a couple of minutes and find out. What time are we getting out of here, by the way?
24.
Okay, good. All right, we got one for lithium fluoride, 848. Okay. All right, 0.2, 848.2 degrees Celsius. How about sodium chloride?
801.
801. Okay. Magnesium sulfide.
1,124.
How much?
1,124.
1124. Okay. All right. So let's give Celsius a little bit of perspective here. Where does water melt at? Melt.
Oh, no.
0. It boils at 100. What is it in this room right now in Celsius, probably?
Celsius.
No.
Why are we doing Celsius?
We're scientists.
Is that like,
Fahrenheit's bad.
I was gonna say, is it because a lot of this stuff is talked about like overseas?
It's because Celsius has a basis on water, which is easy to relate to, if you're used to it. But also, and we'll learn this later, is that it easily converts to Kelvin, which is the actual measured temperature. Fahrenheit is just kind of random. It don't really match up to anything. It's strange, but we're used to it, so we relate to it. If I tell you it's going to be 80 degrees outside, you know what I mean, right? If I tell you it's going to be 18 Celsius, you don't know what that means. You know it's roughly the same thing.
Yeah, I did that one
Well, no, that's the 80s Fahrenheit would be closer to like 28 Celsius.
It said it was gonna be like, it said something along the lines of like 2 degrees, and I thought it was 2 degrees Fahrenheit, and it was 2 degrees Celsius, so. I was poorly prepared.
You had a way too much book. All right, so water melts at 0 and boils at 100 Celsius, and standard conditions, which is considered room temperature, is 25 Celsius. Now, this room is a little cooler than that. It's probably 20 to 22 in here, because our modern comfort, what is room temperature, is a little different than it was back then. Back years ago, before air conditioning, we've gotten kind of used to having it cooler in our room. In the old days, it was either hot summertime, in which you just suffocated all day in your building, or in the wintertime, you had a fire going in the fireplace, which means it was really hot on one side of the room, cold on the other side of the room. So this idea of this nice uniform, everybody in the building sitting at the same temperature thing is very modern convenience. Okay? But in the old days, about 25 Celsius, which is about 76 Fahrenheit, most people don't keep their houses that warm. Yeah, probably my chairs. Some people might keep it that warm, but
My house is always cold.
Yes,
So
I'm
much nicer.
shaking.
well, y'all don't pay the bills, so y'all ain't keeping it. I had a conversation just last night about you want to pay the gas and electricity bill to sleep a little warmer.
Well, I don't care, cause I got a heater. I
Rest
got
of
one
it's-
of those portable heaters, I plug it in.
Yeah, somebody's paying for it too. The argument last night was over 70, and I turned it down to 68 to go to bed. I'm like, I'm not gonna keep it that warm all night, because that was kind of hot. I'd been outside calling ball games, so, see, that's another thing, is it's relative to how much you stay outside, right? So I've been outside all evening, so 70 felt hot. Right, because I've been outside, it was 50, the wind blowing, all that stuff, so then I come in the house and get to bed, and I'm like, it's hot in this house. Everybody else is like, no, it's not. I'm like, I'll turn it down to 68. My daughter's like, it's cold in here in the morning, I'm not gonna get out of bed. So I did turn it up this morning when I got out of bed. 'Cause when I got out of bed, it was, see, and that's all about, how you adapt to it. 'Cause when I got out of bed this morning, I thought it was cold in the house. 2 degrees difference. It's just about, I had been outside where it was 50, came in where it was 70, so that feels hot, right? And then stayed in there for 10 hours. Now it's gone to 68. Now I feel cold. That's 2 degrees. Right?
It's weird. I feel like temperature inside and outside feels like so much different. Like, if it's like
Yeah.
74 outside, 74 in your house. It's
Don't
just-
seem the same.
They don't feel the same.
That has a lot to do with humidity and stuff too. When the wind's blowing.
I need my house cold.
So 74 inside your house in Alabama, and 74 outside with 80% humidity is not going, your body doesn't react.
Because humidity's not for me.
We ought to be used to it.
You would think,
You would think.
but I hate it.
It's rough, especially when you go somewhere.
Right.
You go to Colorado and places like that. It's like,
I love it though, because I went up there and you could like feel your skin burning before you felt like your lungs burning. Love it.
we were in out west a couple of years ago. We left Colorado, drove all the way across Kansas and stuff. Been in the car most of the day. Got to St. Louis late at night, spent the night, got up early, and are driving home. So we've been pretty much isolated from the weather change, right? We get to Paducah, Kentucky, I think it was. We stop to eat lunch. It's like 12 o'clock. Chick-fil-A in Kentucky. And they had just resealed their parking lot, so it's just black. We get out of the car and it's like, oh gosh. Like it was, we could not breathe. Like it was like, we've been out west and it's 10% humidity, 70 degrees all the time. God, like we just drove for 2 days and then get out of the car and it's 98, 150% humidity and the black, hard parking lot. Lord, this is bad.
You think about this, right? I lived in the Midwest, okay?
All right.
I'm used to that. I lived in 12 years, right? And then we went to Disney World in Florida,
Yeah.
okay? And we took a plane to Texas and then to Florida. And when we stepped out, it was like 10 o'clock at night, okay? And it's raining. And I thought it was going to be cool outside. And I stepped out and instantly just like my face is just like, it's warm and it's like rainy. And it's like humidity is crazy.
Yep.
I was about to die right on the spot.
It's a lot of fun when you get out of the car, get out of the truck in the summertime, you've been in an air-conditioned vehicle, you get out, the glasses fog over, You have to just stand in the driveway for 2 minutes, get your glasses, I need a little, yeah. All right, let's knock this out. I got like 2 minutes now, Don. All right, so notice there's difference in the numbers, right? Which one of these is a little more different than the others? This one is, right? little different. These other two are close to each other, right? All right, here's the difference. This is a +1, -1. This is a +1, -1. This is a +2, -2. Okay? All right? We have a little rule here called Coulomb's law. It says the attraction between charged objects increases when the charge increases, decreases when the distance increases. You need to remember that little statement. Okay, not right this instant, but by the more of the next statement, you need to know that. Okay? So what we're saying here is that larger ions make for a weaker bond. Lower charges make a weaker bond. A weaker bond is going to be a lower melting point. So the lowest number up here is 801, okay? Which means this has got the weakest ionic bond. That number tells us this of these three, this is the weakest ionic bond. This is the strongest ionic bond. This is the weakest because it's a +1, -1. And these, the sodium is bigger than lithium and chloride is bigger than fluoride from our periodic treatments. Okay? This is the largest because it's a +2, -2. The sizes here are relatively the same, but +2 and -2 are much more attractive than +1, -1. Okay. Last thing, we'll pick back up with this next time, but just remember, remind me where we left off. We could do this same comparison. We're doing it with melting point. We could use boiling point, which boiling point of an ionic compound is a little bit extreme. Think about boiling, you can. Another term that the AP folks like to use is lattice energy, which is just the energy required to separate the ions from each other, to break up that lattice that we saw a picture of. Either way, whatever numbers you're given, the smaller number means that you have a weaker bond. Okay, we want to talk more next time about the reasons for those bonds being weaker. If the number is higher, it's because it has a stronger bond. And we'll explain some more next time about why those bonds are stronger. All right. I think we're done. Where's my cup of non-distilled water here? Keep your red blood cells intact.
Yeah.